Okay, welcome to today's class. And this is week 10 of our class. Today we will be talking about coaxial cable. And we will cover a little bit of multiplexing, broadband, and baseband. And also that is a common concept that has to do with the coaxial cable is something that's called characteristic impedance. All right, so without further ado, let's keep going with this here. All right. Okay, so coaxial cable, you probably have seen this type of cable. Well, in the past, this type of cable was used to connect the cable TV. That was the most popular, and for some time, it was pretty much mostly the only way we were able to get the cable television. Up till late 90s, then the television started to get the format of a digital signal. So still it was transmitted through the infrastructure laid out before by the coaxial cabling. But now more and more you're going to see, or we'll see more and more things like fiber optic lines, satellite, and such. Okay. However, this is still a popular means of transmitting or relaying a signal. Okay? All right, so let's just start with the quick anatomy of a coaxial cable. The coaxial cable consists of a center core, which is right here. Then we have a metallic shield that also provides, well, you might call it a ground reference. Okay. Now these two parts, that metallic shield and the center core, are separated by a dielectric insulator. Well, dielectric is an insulator, so it's just like insulator, but it sounds nice when you say that. Okay, dielectric insulator. Then the whole thing is sheeted with plastic jacket. So that's the basic anatomy. Now, so different coaxial cables have different layers of, maybe they have multiple shielding and things like that, and the thickness also varies. All right. So over here on the right side, we see a picture of what the cable looks like inside. So over here you see the center conductor or the center core. Over here, there's that white, excuse me, dielectric, then foil shield, and on top of that, you have a braided shield as well. And then there's an outer jacket, right? Now, this is what the cable looks like if you're looking at from basically, like, if you're looking into it, right? So it's a cross section of that. A two-conductor, what is it? Coaxial cable is a two-conductor cylindrical transmission line, typically comprised of a, well, center conductor, an insulated dielectric material, and an outer conductor. Also serves as shielding. Okay. All right, so that's the basic anatomy of a coaxial cable. All right, now just a little tiny bit of the history that has to do with this. What do they write here? A series of standard types of coaxial cables were specified for military uses in the form of RG, and then there's a number, or RG and the number /U. This U, when you see the designation of a coaxial cable, when you see the U at the end, that stands for UV rated. Right? UV rated is basically, you can install this thing outside and you can expose this thing to sun and ultraviolet rays, and it is supposed to withstand that. If you don't have that cable that is UV rated, after about a year or two that is exposed on the outside with the sun shining on it, it's going to turn into some sort of like a degraded sponge. Okay, it's just going to crash. Right? If you touch it, and you can just basically crush it in your hand. That's how strong the UV rays are when they act upon materials that are not UV rated. Okay. Now they date from World War II, and were listed in this type of document here. Now you can Google this and you can see the specifications, and it looks like it was done in 1962. Now these designations are now obsolete. All right, and then by the way, that RG, the cables, the coaxial cables, go by the designation of RG. Okay, so RG stands for radio guide. Mostly they were used for radar antennas. Okay, so the radio signal was transmitted by a transmitter, and it had to make itself, the signal had to make itself into the antenna, and the antenna would transmit the signal to the airwaves as in form of airwaves. Okay, so excuse me. Okay, I guess we're going to hear some noise in the background. Anyways, okay, so now let's just keep going with this thing. Hold on. Thank you. All right. Okay. Let's go back. Sorry. Now, can you hear me now? All right. Now, so that was basically what I was saying, that RG stands for radio guide, and the number that is at the end of the RG designation is basically a number that the engineers who designed those cables, they would be designing different cables serving different purposes, and they would come up with different type of slightly, the cable would slightly vary with their specifications, and they just had to classify them as something that could be defined in some sort of way. So the number you're going to see, RG59, RG6, or RG11, RG58, then those numbers, just treat them as a name. Don't treat it as a number. Do not try to make sense out of why is this thing 59, why is this thing 58. It's just a name. The number is a name, okay, for the cable. All right, okay, let's, all right. Now, the three basic type of cables that we are going to take a look at, these are, I would say, these are the most popular still available on the market. It will be the RG59, RG6, and RG11. Now, the RG6, this is the cable that you're going to see the most. If you have something like a cable internet, and you will see that coaxial cable being pulled into your modem, into your house, or whatever else facility, then you're going to see that type of cable, and usually that is the thickness of that. That's it's a little bit thicker than the size of the, let's say, the Ethernet cable. Okay, so that is that basically you're looking at RG6. Now RG59 is slightly thinner, and the center core has, is also thinner, which is larger number gauge, which means it makes the wire thinner. And then, of course, there is the one on the other side. It's called RG11, and it's a thicker cable altogether, and it has a heavier gauge center core. Okay? And of course, they have braided shield, and there are connectors that are associated with that as well. Okay. All right, applications for these three types of cables. RG59, which would be the thinnest one of them all. And when I put this drawing here, this is the comparison of the thicknesses. Basically, this is how they compare, more or less, in thickness. So there's a bit of a difference in size. Applications for the thinnest cable, RG59. It used to be widely used for the network cabling in the past up till mid 90s. Okay, now the network cabling is utilizing the Ethernet cable, which is the category cable. Mostly right now, you can still going to see cables going to the desktop would be the Cat5e cable. That's the least you're going to see, but quite often you're going to see very popular. Sorry, I'm going to RGs. Okay, it'll be Cat6. Okay, it'll be it's making itself more popular than before. But Cat5e is still very popular. Now video signal mostly in the past, but you're still going to see some cameras or closed circuit television system that is still utilizing the coaxial cable for the video signal. Okay. Now again, all the surveillance cameras, the newest on the market, and the newest, I'm talking about the last maybe 8 years or so. That's the newest. You're going to see a lot of the so-called IP cameras, Internet Protocol cameras. So basically, the only thing they connect to that camera is the Cat5e cable, right? But still, you're going to see some cameras that are utilizing the coaxial cable. They will be the older systems, and there's a lot of them are still in operation. Amateur radio still in use. For RG59 is quite a popular signal that there will be the amateur radio enthusiasts that would utilize RG59 cable to connect their transmitters into the antennas outside. So that's also a very popular cable used in that field. Okay? Then so the frequency limit. Now pay attention to these two last lines. We're going to expand on that a little bit further as we go through this presentation. The frequency limit or the bandwidth of that is about 1 gigahertz. Now, you see, I said I showed the 1 gigahertz in brackets. But I also said something like 1000 megahertz. Well, why don't I just say 1 gigahertz? Well, in telecommunications, there's a technical jargon, and most of the time you're going to see the number, you're going to hear the numbers in megahertz, okay? So that's why I said the frequency limit is well, frequency limit. What's a frequency limit? What's the bandwidth? It's basically the highest frequency you can transmit through this piece of equipment, through this link, through this cable, and the signal would still be able to travel through that and then be understood on the other line by whatever the equipment is receiving the signal. Okay? All right, so the band with the upper limit is pretty much 1000 megahertz or 1 gigahertz. And then RG59, the characteristic impedance, and I put that in red. I want you to remember this because we're going to talk about this thing in the next few slides. Characteristic impedance is 75 ohms. Okay. Now, then we go to RG6, which is the one that you mostly see when you have the internet installed in your house. That would be the RG6 type of a cable. Now, it used to be widely used in cable television. Maybe in some rural areas, still there is some equipment that utilizes the coaxial cable to distribute the television channels, but now most of the time you're going to see the digital signal transmitted. Still, it can be transmitted through the coaxial cable because the infrastructure still be there. But most of the time when there's new construction going on, new installations, most of the time you're going to see fiber optic lines laid right to the house or to whatever facility. CCTV, what CCTV stands for? CCTV is closed circuit television system or closed circuit television. CCTV could apply to video surveillance, which is, in other words, there would be security cameras around the building or inside the building. So that's closed circuit television. And quite often when you are in your high school, if your high school carried the broadcasting class, quite often still you would see the television sets or the monitors being fed with coaxial cable, which is part of the closed circuit television. That transmit, what they would transmit, like maybe every Friday, the broadcasting class would prepare a program, which would be the school news and whatnot, and that would be transmitted over the closed within system that doesn't go outside of the building. So that's a CCTV, closed circuit television. And then, of course, it is it is used in internet delivery. And in brackets, I put broadband. Okay, so keep that in back of your mind. So the broadband, the terminology broadband, okay, the bandwidth or frequency limit, and characteristic impedance. Okay, we will expand on that. And of course, the RG6 also is being used to provide signal as a radio guide, RG6, radio guide number 6, okay? A radio guide to deliver the signal from a transmitter or communication device right to the antenna. Okay, it also could be a receiver, so it could be transceiver, transmitter and receiver in one box. All right, then we go to, okay, so we can see here the frequency limit or the bandwidth of that, of the RG59 is 1 gigahertz or 1000 megahertz. And also for RG6, you have the upper frequency limit of transmission would be also 1000 megahertz. So why would you use one or the other? Well, as we go towards the end of the transmission, as we go towards the end of this presentation, it has something to do with the attenuation, okay? The RG6 cable can carry the signal a little bit longer and attenuate. Attenuate means degrade the signal, make it smaller to the point that it's unusable. So RG6 can carry the signal for a longer distance than the RG59. But still, the frequency bandwidth, the frequency upper limit is 1000 megahertz for both of them. Now, then we go to RG11, which is the thickest cable. Then again, it was used mostly in the past, but still maybe you're going to see some instances that you're going to see cable television, closed circuit TV, also internet, and then in brackets I put broadband and antennas, and then you can see because of the greater physical parameters of that, there's a thicker cable being used, which means less resistance, and there is a little bit more separation as far as distance. So all those factors, they contribute to better frequency limit, better width. So it's 3 times as much, 3,000 megahertz or 3 gigahertz. Now, the characteristic impedance of that is also 75 ohms. One thing that I did not include here is a cable that's RG58, which would be basically almost as thin as the RG59. But the RG58 has a different characteristic impedance as opposed to 75 ohms. That one has the characteristic impedance is of 50 ohms. And if you are confused, don't worry about it. If you're wondering about what the characteristic impedance is, we will talk about that. Now let's see here. Okay, I'm gonna stop here and talk about the characteristic impedance for a second. Let me just lower the lights so we can see the marker a little bit better. Okay. I'm not sure if you had some of the telecommunications course or circuits, did you cover the AC theory or not? However, I'm just going to say, all right, let's say this is one of the circuits that would be utilizing AC power supply, and that will be connected to a resistor, that will be connected to a coil, and then maybe that will be connected to the capacitor, and will be closed right into here. So here's the AC source, resistor, coil, and see, that will be typical RLC in series. Okay, now the capacitance of that, what's a capacitor? A capacitor is a device or a component that utilizes plates, and they're separated by dielectric environment. It could be air, or it could be other things that separate, that are not supposed to conduct electricity. What capacitor does, if you have minus and plus here, if you polarize the capacitor like that, of course the electrons are going to gather on this plate, and they won't be able to, they will not be able to travel through the dielectric environment into the positive plate. Now, if you reverse the polarity, the electrons are going to disappear from here, and they're going to flow through whatever wire, and they're going to, or power supply here, they're going to gather on here. All right, so with AC, the capacitor is working as just basically, that's the basics of the capacitor in a few seconds, if I could say. Now, the capacitance of the capacitor depends on the distance between the plates, and also depends on the size of the plates. So if the plates were smaller, right, just like that, the capacitor would have something that's called less capacitance. All right. Now, if you expand the plates, make them bigger, the capacitor will be able to handle more charge, so the capacitance value would be greater. Okay. Now, of course, we know that when it comes to capacitors, capacitors have a high resistance. I didn't. It's not a mistake. I said the word resistance. They are resistant to current flow when the current goes, when the frequencies go less. So if the frequency basically is 0, or in other ways in infinity, but let's not talk about that. If if you have a completely DC environment, it's a DC power supply, there's no frequency going on, then the capacitor is going to be present a total resistance. It's just not going to conduct. Now, if you start deviating from that and introduce a little, maybe low frequency, then the capacitor is going to have less resistance. So the higher the frequency, the less resistance the capacitor is going to give you. However, the capacitor also naturally is going to have some internal resistance. So it's supposed to be the resistance. Yes, it's going to have some inductance, but it's negligible, so let's forget about that. Now, the combination of the resistance and the reactive resistance, because capacitors are reactive, their resistance depends on the frequency. The higher the frequency, the less resistance capacitor is going to be. The lower the frequency, the more resistance the capacitor is going to give you. So, so it's called a reactive resistance, and basically we'll call this impedance. Okay, so the difference between the impedance and the resistance is always constant, and the impedance is a reactive resistance that depends on the frequency. So resistor, doesn't matter what frequency you put in, resistor is going to give you a constant resistor. If it's a 10 ohm resistor, it's going to give you 10 ohm resistance, whether you put 10 hertz to it or you put a million hertz to it, it's going to give you 10 ohms. Now, when it comes to impedance of a capacitor, then the impedance is going to depend on what frequencies you apply to that. Okay. Now, so this is if you put a capacitor in the circuit and you have a constant supply of an AC source. So that would be the impedance of the whole system, of the impedance of the capacitor or impedance of the RLC circuit. Okay, so that is the impedance. But remember when we were talking about something that's called characteristic impedance. See that? The characteristic impedance also implies impedance. However, it's not. It doesn't work quite as this circuit here. But first, I have to give you the concept of what impedance is. I hope I was kind of clear on that. If not, send me an email or talk to me. I'll explain this thing to you in a greater detail, or you might actually cover this thing with other professors in our college or wherever else you're going to study things. Okay, now, characteristic impedance. Let's say we have a transmitter, and we're going to represent that with a box. Okay, so that would be the transmitter. The transmitter would have whatever circuitry, let's not get into that, but it's going to have an output. Okay, that's going to be the output. And let's say this output is going to be connected to a coaxial cable, and that thing is going to be connected, well, just a magnified version here. And this coaxial cable is going to be connected to, let's say, an antenna. Okay. Now, when it comes to transmitting radio waves, okay, so we're talking about radio waves. Now, imagine that you have a bucket of water, or maybe like a little pond here, okay, so there's water here. You drop a little stone here, the stone hits the water, it's going to create waves, okay. Now the stone is going to drop right to the bottom, but the waves continue. So that little stone, that little pebble is not connected in whatsoever to that surface of the water, but the water is still making waves. So we're initiating a wave, okay? And the wave continues all by itself after the little stone is not in the picture at all. So same idea here. The transmitter is going to look at the input of the radio guide. Now, remember when we looked at the anatomy of the coaxial cable, this is what the transmitter sees. And all the transmitter cares about is how difficult or how hard it is or how easy it is to insert a wave into this radio guide, into this cable, and once it inserts the wave carries on its own. So here's the concept of the characteristic impedance. The transmitter only sees the input of the transmission link. It is going to insert the wave, and the wave is going to continue on its own, and depending on how strong the wave is, and depending on the characteristics or the specifications of that cable, that wave is going to continue. Of course, it's going to keep getting smaller and smaller as far as the distance goes, but the impedance that the transmitter sees is only the impedance on the entrance of this link. So, based on what I just said, that's the characteristic impedance. So I'm going to ask you a question. Do you think that the characteristic impedance, okay, you know what? Let's just back up a little bit. Remember when I showed you what a capacitor is? There are two metal plates separated by a dielectric. Okay. Now, if you look at the cross section of the coaxial cable, you have one piece of metal, and that continues just like that. And it's separated by a dielectric, and it's surrounded by another piece of metal. So basically, it's just like having two plates of a capacitor. They're just different shape. They are not just, you know, two flat pieces of plate. However, there are two pieces of metal separated by a dielectric. So yes, they're going to have some capacitance. So the capacitance of the cable is going to, total capacitance of the cable, if you will, is going to change with the length of the cable. However, since the transmitter only cares about inserting the signal into this cable, and that's the only thing that says, I'm just trying to see how big the opening is and how easy it is for me to insert the signal. Do you think that the length of the cable is going to change the characteristic impedance of this cable? Yes or no? Does the characteristic impedance depend on the length of the cable, based on what I just said? Anybody? I hear crickets. Are you guys afraid to? I would say so. Okay, so here's one answer. Okay. Well, Louis, thank you for being brave and answering. So I really appreciate that. However, the answer is no. Okay, because the transmitter only cares about how difficult it is to insert the wave into that, and then the wave continues. Yeah, the wave continues on its own. So it's just creating a wave, and now we can disconnect, and the wave is going to continue by itself. So the characteristic impedance is the impedance based on the capacitance of the entrance, only the entrance. How hard is it to insert the signal, and that's it. So it doesn't depend on the length of the cable, but it would depend on the sizes of the core, of the metal core, or the center core, and maybe the size of the plastic jacketing. Okay. And the distance between them. Right? So characteristic, and that is going to be on the test for sure. You can count on that. Characteristic impedance does not depend on the length of the cable. That's why it's called. That's why the terminology has to be distinguished. So whoever was working on the terminology, they just decided that we have to change the name of that a little bit to distinguish between that type of impedance and the total impedance of the whole system. So so the characteristic impedance does not depend on the length. That's why it's called characteristic impedance of the cable. Okay. All right. So we have covered that. Here. Now, Broadband connection. First, I'm going to talk about broadband connection, and I'm going to tell you what broadband is. All right, so it's just a little bit backwards, but I think there's a reason for that, and I don't remember what it is, but I decided to put those slides a couple of years ago because, and then I'm going to find out later on. Anyways, broadband internet service is the most used from the internet access because of the high access speed. So high speed is associated with the broadband connection. It is offered, so broadband internet service, for example. Okay, so broadband internet service is offered in this type of forms: DSL, which is a telephone line, digital subscribers line, fiber optics, cable, satellite. Okay. Now the old dial-up connection, which would be the old dial-up modem, is the only non-broadband internet service that is available. And even though that it is cheaper or less expensive, most internet users are moving towards the faster broadband internet connection. Now, I think it was last time we talked about it. Ethernet and internet. Okay, internet, the signal type that's provided to your house is in an analog form, and the Ethernet, which is the connection between the switch and on your computer, it is in the form of, it's a digital signal. Okay, so in digital signal, TDM or time division multiplexing or baseband is applied. And in internet signal type, an analog, the best delivery would be frequency division multiplexing. Okay, now, what does all this mean? Let's take a look at this thing here. All right, broadband. Okay, now if you look at these two scenarios here, this would represent the broadband type of multiplexing, and this would represent the time division multiplexing. What is a multiplexing? Multiplexing is basically discrimination. It's a discrimination. How do you discriminate a signal? How does a radio receiver discriminate what it wants to receive? Because the biggest thing that we have in contact, you're in contact with it now, would be a air. Okay. There are multiple radio stations transmitting their signals all over the air, and the air is basically containing all the different frequencies being transmitted from different frequencies, and they all exist stronger or weaker at some point, but they all exist at this point. If I put a radio receiver right here, and if I discriminate on which frequency I want to tune my radio receiver to, we're going to receive that particular radio station. So that would be the frequency division multiplexing. Okay, frequency division discrimination or tuning towards. So if there is a radio station that transmits their carrier frequency on certain frequency, or the carrier on certain frequency, then I can tune my radio receiver to that carrier frequency, and I'm going to pick only that frequency out of all the frequencies that are present in the air. Okay, so that's called the frequency division multiplexing. Okay? So in frequency division multiplexing, so that we're talking about the air, but since, remember, RG, the RG designation of the coaxial cable stands for radio guide. So instead of transmitting the frequencies or radio frequencies through the air, when you have coaxial cable, you're containing them right into that cable. So it's just like having the air transmission, but you're not transmitting it through the air, you're transmitting it through the cable only, and it's contained within that cable, all the frequencies, all right? So let's say the old way of transmitting the television channels, the old way would be, up to mid-90s or so, or late 90s, all the frequencies, all the channels that would be transmitted from the television station, all the channels would be in that one cable. And then on the receiving end, you would have a tuner on your television, and you would tune to a specific frequency that is still there, and they're all at the same time in the cable. You would just pick which one you want to receive by adjusting your tuner on the television station, on your television. That's why one of the biggest differences that people who still remember the old cable television, when you had the remote control, when you flip between channels, you would get an instant channel change. It would be just with the flip of the button, before you release the button, the channel would be changed. It would be just like bang, bang, bang. The channels would be switching because the tuner was just so fast and the frequencies were existing on that cable. Now with the digital signal, you press, and it takes about maybe a quarter of a second or so for the frequency to for the signal to switch from one type of signal to another. Okay, with the digital transmission. Now, so this would be the coaxial cable that would contain 1, 2, and 3 channels. Okay, and they will be all existing at the same time in that cable. So let's see what we have here now after I explain what I just did. Broadband connections are divided into channels. So channel 1, channel 2, channel 3, and each has their own frequency. So let's say there's 1,000 megahertz or 1 gigahertz of frequency from low frequency to the higher frequency, and channel 1 would be somewhere here, would occupy from certain frequency to certain frequency. That will be channel 1. Channel 2 would be here, will be different frequencies, channel 3, and so on. Okay, so all of them are present, all the frequencies, all the channel, all the carriers are existing in the radio guide at the same time. Okay, so the connections are divided into channels, and you tune into whatever channel you desire to receive whatever signal you want. Each channel occupies a space within all the spectrum that the medium, in this case is cable, can handle. So again, each channel occupies a space within all the frequencies that the cable can handle. Okay? It has a little slot between the frequencies, well, within the frequencies that are available on that cable. All channels are injected into the medium, which would be the cable in this case, at the same time. They exist simultaneously in that cable. Communication between devices is established through tuning to a specific frequency. So in frequency division multiplexing, all the channels are there. You just pick which one you want by tuning into whichever one you want to go, but they still exist at all times. So this is considered as frequency division multiplexing, or discrimination, or choosing something. Okay, now baseband. So this will be broadband. Now baseband, there is no channel division. Okay? Time sharing is implemented. So each communication link occupies all the bandwidth that the medium can handle. So if you want to transmit 10 channels on the coaxial cable, let's say 10 channels is something dreamed up. Usually there's more than 10, it's like 100 of channels. But let's say 10 channels. All those 10 channels have to exist. So from whatever frequency to whatever frequency to whatever frequency to whatever frequency, that cable has to be able to handle from the lowest frequency to the highest frequency. It has to be able to handle the transmission of those frequencies. So the bandwidth of that cable has to be high. Okay? Now, when we're talking about time division multiplexing, yeah, we are not injecting all channels or all signals at the same time. Okay, the channels are being transmitted through that link on time division basis. So let's say second number 1, I'm transmitting one type of a signal. Second number 2, I'm transmitting another signal. Second number 3, there's another signal. And second number 4, and there's another signal. That's the transmission part. Now, the receiving part of that, the receiver will have to be synchronized with the transmitter. So when the transmitter is transmitting the first signal, it has to synchronize with that. So it's receiving the first signal and is directing it to, let's say, one telephone set or one television channel or whatever it is. Then when there's another second goes by and there's a second, all right? Then there's a different signal being transmitted, and that receiver knows that this is the second signal, and that is a telephone conversation between that person and that person. So I'm going to direct that signal to the other person. Let's say it's a telephone conversation. Now, second number 3 passes, and during that second, there's a third signal being transmitted at that time, and it's between that person and that person. So the receiver is going to connect these two people at that time. Now, if you make that switching extremely fast, okay, that person and that person that is only using the certain times of the cable, it's a time sharing of the cable, but if it's happening extremely fast, it's going to sound like the conversation is continuous. Okay, so that's the time division multiplexing. But then in this case, that cable or that link or that medium is not required to have a high bandwidth to accommodate all the channels. It's only required to have enough bandwidth to transmit one channel. So there's not a requirement to have a high bandwidth on that cable. I'm looking at the time. Okay. It's just supposed to you're supposed to handle enough bandwidth or enough frequency reliability that is supposed to transmit only one channel. So the bandwidth is not a huge requirement on that, but the switching is because the switching is implemented. Okay, so that's the difference between the broadband transmission or baseband transmission. Okay, now let's see what we have here. In baseband, there is no channel division, as there is channel division in broadband. Okay, now broadband, each channel occupies space within all the spectrum of the medium. Now each communication link occupies all the bandwidth that the medium can handle. That's what I said. It's supposed to handle only one channel, yeah? Because time sharing is implemented in this case. Now, in baseband, each communication link waits its turn to talk in a time-sharing manner. Okay. And in the baseband, no tuning is involved. Well, maybe it's a lie. Yes, there's tuning involved, but the tuning doesn't switch. The transmitter or the receiver is tuned to the transmitter, and that's it. It stays that way. And everything else, the channel division, is done by time sharing. Okay? Now, no tuning is involved because the signals are not assigned to channels. So that's the time division multiplexing. Keep going. Dial-up modem, because remember I said that most of the internet is provided to you by broadband. However, there's a dial-up connection that is still being used. You might think that dial-up is not used anymore, but it's still being used. Okay, and that's the only one that is not implementing the broadband as far as to provide the internet. It's basically a one-to-one telephone connection. Okay? All right, and that's what the old dial-up modem looks like. Those things are still being produced and still being used. And when you download this thing, this presentation here, you'll be able to click maybe, and this will direct you to a YouTube channel that would give you the sound of the dial-up modem. And I have one of those here, and basically that's what it sounds like. Where is it? Okay, hold on, guys. I gotta take care of something really quick. I'll be right back. Give me 2 seconds. Okay, I'm back. What do you know? We technicians here upgrading our internet, and if I didn't stop them, we would lose our internet connection. Okay, speaking of the wolf. All right. Now, where were we? I was going to find you the sound that the internet, the old dial-up internet makes. You probably don't know that, but I just had that thing queued up. History. That's what it sounds like. All right. That's what this thing sounds like. That brings some sentiments to some of us. All right. Now, is this thing, now it's a slow internet? Okay. Is this thing being still used? Yes, it's still being used. How does it work? Well, here is whatever the communication company here, local exchange, and here's there will be the server that this modem needs to connect to. It selects, it goes over the phone line, selects, dials up the phone number of whatever the server is connected to, makes a connection, and then the connection is made and whatever the signal transmission. It's a slow connection. It's still being used. Where is it being used? If you get a job as a technician in telecommunications, is this modern type of telecommunications, where would you see that? Well, you would see this thing in a situation like this. Let's analyze this picture really quickly, okay? Here is the patch panel that has the field wiring that goes to wherever the could be, let's say it's a store. There are a bunch of cash registers that are connected, terminated through the Cat5e wires into the patch panel. Then the patch panel is patched through the patch cables into the switch, and the switch is connected to a gateway and then that thing is connected to the modem, and you have a internet connection for those cache registers that basically, remember, they're connected to VPN if it's a store chain, and then all the transactions are being registered in whatever the main company is registering. Okay. Now let's say there's something wrong with the internet provider or the network or whatnot. Okay. So let's say I have 5 cache registers in the store, and they're all utilizing network for their debit transactions and whatever communication they need to have established. And let's say the internet goes down, or something happens to the network. The gateway goes bad, or whatever it is. The network doesn't work. There's no connection. The store is still open. So what happens is that there's the so-called backup connection, backup dial-up modem. Very popular in some of the stores. Sometimes you might see the situation that, there's 5 cache registers, but all the 4 cache registers are not working. There's only one, and it's going really slow. Okay, well, that's what happens when the network gets lost, interrupted. So there's automatically the whole system switches to the backup dial. So, excuse me. So it's still, the connection is slow, but it's possible to maintain the operation of the store. It is slower, but the client still can come up to that one designated cache register, that it's all the other cache registers are offline. That one takes over, and the only one, it's a backup, and it's using the backup dial modem, and the transactions are slow because every time you use a debit or credit card, that cache register uses the dial-up modem, dials the number, makes a connection, makes a transaction, and then hangs up and whatnot. Okay, so so you're still going to see some of those, right? Some of those modems. Okay? Quickly now, if you have to go, guys, then by all means go. If you have another class to attend, I just have a few minutes to finish, maybe 3 or 4 minutes to finish this presentation, and then I'm going to see you in the lab at 1 o'clock, I think it is. So then I'm going to post this thing on YouTube, and you'll be able to see the end of it. So if you need to leave, by all means, please do so. Okay? Now, remember when we were talking about the characteristic impedance and the bandwidth of the cable? Here's the RG59, here's RG6, here's RG11. Let's look at the bandwidth. Okay, they all have the characteristic impedance of 75 ohms. Now, the one thing I need to mention, in order for the maximum power transfer, you're going to have that in some of your electronics classes, the impedance of the transmitter has to match the impedance of the link, and it has to match the impedance of the transducer. Right? So then there's maximum power transfer that goes, the signal can pretty much travel in the most efficient way through the whole link. If the impedances are mismatched, it will still might get some signal through, but not as much. And where all the other energy, all the rest of the energy is going to end up, it's going to end up as heat, and then you're not going to have, like, if it's a case of a transmitter, then you're not going to have a transmitter transmitting at its full power. Okay, so it's important to match the impedances. So the characteristic impedances of all these 3 are 75 ohms. Now, remember I said, okay, so 59, RG6, and RG11, the RG59 and RG6, they have the same bandwidth, okay? So they are able to transmit frequencies up to 1 gigahertz. Now, RG11 up to 3 gigahertz. So what's the difference between these two? Well, here's this slide here. Attenuation. And of course, there are conditions, 20 degrees Celsius or 68 Fahrenheit. And there are frequencies here. Okay, 5 megahertz, 55 megahertz, and so on. The frequencies go up. So this is the lowest frequency that we're studying here. This is the highest frequency that we're studying here. Now, and there's the attenuation, which is basically the signal loss, the signal deterioration. Okay. So per 100 feet. Okay. Now, dB, that stands for decibels. It's a logarithmic type of a scale. All I'm going to tell you is that decibels is a reference type of a unit. So if you have a signal, okay, that's all you need to know for this type of presentation. If you have a signal of certain strength, you raise that signal 3 decibels, you're doubling the power of that signal. Or if you lower that signal 3 dBs or 3 decibels, you are cutting the power of the signal in half, okay? So if you have a 100-watt signal, you raise it 3 dB, you're going to have 200 watts. Now, if you raise 200 watts 3 dB, you're going to have 400 watts, and so on, okay? So that's just as far as me giving you some understanding on the decibels loss, okay? Now, so when we go talking, different frequencies are attenuated in a different way. So some of the lower frequencies have enough power, so they are not attenuated as much as the higher frequencies, because the higher frequencies have less energy, and if something has less energy, then obviously it has less energy to penetrate that type of physical environment, that in the form of a cable. So let's say here 5 megahertz, the attenuation per 100 feet, RG59 will attenuate 0.89 of a decibel. Remember, 3 decibels is half the power. Right? So, so per 100 feet. All right. Or also you have per 100 meters. Okay, 100 meters is much longer than 100 feet. So if you go 100 meters, the lower frequencies are going to be cut in half as far as power or energy maintained within that signal. Right now, 5 megahertz, that's the low frequency. Let's say 3,500 megahertz, all the way up there, well, the bottom here. So the RG59 is going to attenuate or deteriorate the signal by 16 decibels. Remember, 3 decibels is half the power. So that's pretty much not bad of attenuation, or bad attenuation, okay? So then let's say compare that to RG6. So 5 megahertz per 100 feet, RG59 is going to attenuate the signal or degrade the signal by 0.89 dBs. RG6 is going to attenuate less. So the signal degradation or signal loss, or the power loss of the signal, is going to be less with RG6, okay? And it's going to be even less with RG11, right? So big difference here. Let's go all the way up with the frequencies here. RG59, 35 megahertz, is going to be attenuated 16 decibels per 100 feet. Now RG6, 12 decibels only, and RG11 is going to attenuate only by 8.28. So that's, and you can analyze this thing once you download this presentation. So that's how things work. So basically, low frequencies, as the, well, if you have music, that'll be the bass. They have a lot of power, a lot of punch through. So they're going to carry the energy longer through that cable. So lower frequencies get destroyed or degraded or attenuated less. All right? They can travel longer distances over the cable. The higher frequencies have much less energy, so they are not going to be able to travel as much or as far, right? So there's that kind of a slope, okay, or attenuation slope. The attenuation for lower frequencies is less. The attenuation for higher frequencies is more. Here is the signal is going to stay strong for longer distance, it's not going to stay as strong over longer distance if the frequencies go up. Right? So that's the idea of a slope. All right, now let's keep going with this here. This is the channel division for cable TV. I would hate to say it, but it's almost obsolete right now. However, the TV channels still exist. So that would be the frequencies that will be occupied by the TV channels. So channel 2 would occupy the bandwidth of between 54 and 60 megahertz. Right? So you can see there's a 6 megahertz space out of the whole frequency spectrum. 6 megahertz is going to be designated for one channel. All right, next channel is going to occupy next 6 megahertz. All right, channel 3 goes from 60 to 66 megahertz, and so on. You see there's 6 megahertz slots. So therefore, that will also enable you to understand the frequency division multiplexing, okay? Now, the last picture is something that's called an RF amplifier or radio frequency amplifier. I'm going to quickly analyze this thing, and that's why I explained the slope a little bit, okay? Now, the radio frequency amplifier is a very simple device as far as to connect. It has an input and it has an output. That's the main two things. These are the main working. Input, and it has an output. And of course, because it's an amplifier, it has to have some sort of like a, some form of a volume control, all right? So here's the control, that's gain. So you have a radio frequency or cable TV bundle that is going into that radio frequency amplifier. And there's a gain in order for us to establish certain amount of signal strength on the output of that. Now that output of that radio frequency amplifier can be connected to a longer vein or a cable that transmits the radio frequencies or the channel TV channels over that. And further it gets away from the amplifier, the less strong the signal would be, the weaker the signal would be. And then let's say it's a school environment. The big cable goes through the hallway and there are classrooms. So there will be classrooms that will be tapping into that main, in the bus configuration, signal. But the signal that needs to be delivered to a television set, it cannot be a really strong signal. It has to have a certain strength. If it's too strong, the channel is going to become too strong. It's going to look not pretty. Right? If it's too weak, it's also going to look not pretty. It has to have certain strength. Now, there will be taps, so a different type of taps would be tap in, and the taps would have certain amount of attenuation. So the taps would attenuate more because the signal is extremely strong towards the beginning of the run. So you have to attenuate the signal more. So you have to weaken the signal more so the television is not overpowered with the signal. And then as far as you go, the further you go, there will be a signal loss in the cable because of the distance. And then the tap would be less attenuating tap that is supposed to deliver the signal to the television set. Right? So that's how basically it works. So the signal that is coming into the amplifier here has to be adjusted in certain strength so it has enough signal to carry to the furthest point. Right? And then the taps would be chosen accordingly to deliver the signal strength to the TV. All right, now, because the cable TV or the cable, the coaxial cable, attenuates frequencies, different frequencies at a different rate. So the high frequencies are attenuated less over the distance than the low frequencies. So towards the end of the run, if it's a long run, you're going to see some of the lower channels or the lower frequencies coming still okay. We're going to have a pretty clean signal. However, some of the higher frequencies are going to come a little bit weaker. So you're going to see a weak signal on the TV. Right? The further away you go from the amplifier. So what happens is that you need to adjust, because that's a naturally occurring slope. Okay. So in order to compensate for that, you are going to adjust the slope on the amplifier, and in this case, the slope is labeled as tilt. It's the same thing. Right? So then you're going to amplify the higher frequencies way more than the lower frequencies. So by the time you get to the end of the channel, the end of the run, the frequencies are going to be sort of like equally strong. So the lower channel frequencies are going to be nice and clean on the television set, and the higher frequencies are going to be nice and clean also on the television set. Right? So there's a balance between how strong you want to push that signal, and depending on that, how you want to adjust the slope or the tilt of that. So sometimes it's this thing is this control is labeled as a slope or a tilt. Okay, and of course over here you have minus 20 dB test, and then you have a minus 20 dB test signal. So if the signal is really strong, you get that you connect your television set straight into this one here, into this output, and it gives you this extremely strong signal is brought to a manageable signal strength that the TV can handle. And on the output as well, there is a 20 dB test output. Okay, so but the main two connections is, here's the input, here's the output, here's the gain, and here's the slope. So if sometimes you're still going to have service calls that have to do with different signal strength on different televisions. Some of those earlier, well, maybe years ago, installed systems, they were pretty expensive systems. So if somebody spends like $200,000 on a system, they're going to try to run it for as long as they can, so they don't have to spend another $200,000, maybe because that system was only installed 10 years ago. So you're still going to see some closed circuit television systems in some facilities. So if you have something like that, for example, a service call that you get called in, and you say that, well, there's some television sets or some monitors are receiving some of the lower channels are okay, but some of the higher channels are really bad, and it used to be okay. Well, your first question would be, did you change anything? Did you add any televisions or television sets into your system? Oh yeah, last summer we just wanted to have, because now that room used to be a storage, and now we made it into an office, and we needed another TV over there, so we just get a splitter and we just put that thing. Well, you throw the whole thing out of balance, okay, because then you split the signal in half at that point, so anything past that point is not carrying as strong of a signal as it used to. So so basically that's I give it a heads up. If you have that type of a service call, you're going to see less and less of those anymore. However, you still are going to be able to you still are going to be seeing something like that. And there's a difference between knowing what to do or knowing how to approach that type of a service call, and being able to make money on it, or not knowing what to do and walking away from it and not being able to make money on that. It's all about money, okay? Plus, the more you know, the more valuable you are. Okay, so that's pretty much it for today's class, and I'm going to see some of you at 1 o'clock in the lab. Of course, bring your side cutters, safety glasses, and that's pretty much all we need for this. Remember, side cutters is the most basic tool. Permanent marker always as well. So if you have these two tools, you're okay for my labs. I'll try to teach you how to perform most of the operations just using these two basic tools. Later on, if you find yourself a job dealing with this type of installations or terminations or connections, you're going to build your own arsenal of tools that you are comfortable to use. But if you know any, because side cutters you're always going to have with you, I'm teaching you how to accomplish the most using the least amount of tools. Okay. All right. That's pretty much it. And I'll see you when I see you. And thank you. And I'll see you next time. Bye.